Liquid mirror telescope technology. Introduction. Liquid mirror telescope technology is a fairly new and rapidly progressing technology that already shows a huge potential, reminding us of the need to never stop improving the telescope technology we use today. Liquid mirror telescopes are telescopes that use reflective liquids such as mercury instead of solid glass as mirrors. The history of the liquid mirror telescope can be traced to Ernesto Capacci of the Naples Observatory in 1850, who described the concept of a parabolic mirror formed by rotating a vessel of liquid mercury. He did not follow up on this idea, and it was not until 1872 that an English astronomer, Henry Ski, built the first working liquid mirror telescope with two different but equally successful techniques: an electromagnetic engine and a small hydroelectric turbine. Further research was needed to build a high-quality instrument that could be used for astronomical purposes, and only 35 years later, Professor Robert Wood of Johns Hopkins University began experimenting with the idea of the mercury paraboloid as a reflecting telescope. While he was able to obtain photographs of two double star systems and published 3 papers in 1909, he did not pursue the idea of liquid mirror telescopes further due to restrictions of the technology. The 1980s brought a new wave of interest in the technology due to a Canadian researcher, Armando Borra, who, together with his colleagues, built on Wood's findings and conducted optical tests that showed that large, direction-limited mirrors are a reality and can have practical astronomical applications. When the use of large diffraction-limited mirrors was successfully tested in the lab, the researchers focused on applying this technology to real-world scenarios. Liquid mirror telescopes have seen limited adoption since the 1990s, with the biggest telescope to date, a 6-meter Large Zenith Telescope, used for atmospheric measurements and operated by the University of British Columbia in Vancouver. A project called the International Liquid Mirror Telescope is under development at Devasthal, India, and the feasibility and potential of using liquid mirror technology for large telescopes on the Moon are being explored. Such telescopes could provide more detailed images and detect objects 100 times fainter than the James Webb Space Telescope. Advantages and disadvantages of using liquid mirrors. The use of liquid mirror telescopes in real-world scenarios highlighted their advantages and disadvantages compared to solid glass mirror counterparts. The biggest advantage of liquid mirror telescopes is their cost, with the use of liquid mirrors cutting down the cost of the telescope up to 98% compared to solid glass mirrors. The second advantage is a simpler and lighter construction, which can be assembled faster than a traditional telescope and requires easy maintenance. Both of them make liquid mirror telescopes an economically viable option for educational and research in spite of potential budget constraints. The biggest disadvantage that limits the widespread use of liquid mirror telescopes is that they can only be pointed straight up, otherwise, the mirror will lose its shape. Because of this fact, all the current liquid mirror telescopes are zenith pointing. Since liquid mirror telescopes cannot be tilted, this proves a challenge for physically tracking an object. Only brief digital tracking within the telescope's fixed point of view is possible. It should also be noted that mercury, the inexpensive metal typically used for liquid mirror telescopes, is toxic to humans and evaporates at above normal temperatures. This fact emphasizes the importance of safety and highlights the need to search for safer and more efficient alternatives. The physics behind the liquid mirrors. How can metals be used as liquid in the mirrors? As mentioned before, the principal metal used in liquid mirrors is mercury. Several of other metallic candidates were examined, such as ionic liquid coated with silver, which wouldn't evaporate even in vacuum, allowing the use of it off Earth. Another material proposed is made of magnetic iron particles, ethylene glycol, and a coating of silver nanoparticles, which showed better reflectivity and stability than mercury. Concaving the liquid mirrors in the desired curvature. As Borra puts it, the curvature of liquid mirrors follows equipotential surfaces, which can be shaped by rotation to yield paraboloidal surfaces. The liquid metal is held in a container which is rotated in a gravitational field. The rotation around a vertical axis is performed at a specific speed, and the shape of the container, which is perfectly horizontal, is very close to the desired shape of the liquid metal to reduce its amount. The shape of the liquid mirror is therefore created by the natural equilibrium of gravitational forces. Another way to affect the shape of a liquid mirror involves applying magnetic fields of ferrofluids to achieve the desired shape. In practice, the primary mirror focal ratio of the Large Zenith Telescope is f/1.50, with an effective focal length of 10,000 meters. It uses a 4-element refracting corrector lens with the diameter of the corrected field of 24 arcmin. The liquid dish is rotated 7 times per minute, and this exact number distributes the mercury into a 1 mm thick parabolic layer. The mirror's outer edge has a velocity of just more than 2 meters per second. The telescope uses 2048 by 2048 pixel CCD as a detector with a width of 16.9 arcmin and 0.495 arcsec/pixel image scale. The optics of a liquid mirror in a typical telescope. Henry Ski was the first to produce the mathematical formula that defined how the focal length of a liquid mirror telescope could be. F equals G/omega 2. In this formula, F is the focal length, omega is the mercury's angular velocity, and G is the local gravitational acceleration. This formula was further improved by Wood, who amended it to be F equals G/2 omega 2. This was also the formula used by Bora to describe the relation of the focal length of the mirror F to the acceleration of gravity G and its angular velocity omega. No other factors are accounted for. For example, the liquid density does not affect the focal length. Conclusion: liquid mirrors are an important step in the development of next-generation telescopes and provide new, exciting opportunities for astronomers all over the world. Their advantages outweigh the disadvantages, and their low costs, large sizes, extremely high optical quality, and numerous other features can enable projects which were impossible in the past due to impossible costs. This makes them a potential competitor